Hello, and welcome to a brief demonstration of the incremental checksum guard that's included in our Denali platform release. Now, we all know that security considerations must be carefully balanced with performance considerations. Sometimes app owners can lose sight of this, though. And as a result, when they see that the security they've added to their app slows down app performance, they turn the security off completely. Now, at Digital.ai AppSec, we've long been able to avoid this outcome by adding the ability to finally balance security with performance considerations. So the ability to finely tune performance and security creates the need to do iterative tuning, especially in high performance applications, which require maintaining a high frame rate. In the past, if our customer wanted to check some large chunks of code in a performance sensitive app, they needed to break up the protected range into pieces that were small enough to fit in their performance budget, and then schedule checksum invocations to make sure that the right checks were happening at the right time. This approach required multiple passes to get the partitioning right. It was doable, but it was labor intensive. With the new iterative checksum, a customer can look at the entire protected range as one piece to determine the total time needed to checksum. Then they can divide that time by the time slice available per frame or per execution unit. That quotient is then used to specify the number of slices for the iterative checksum in one step. This allows the customer to save all the time that was required to do the manual partitioning and the time needed to do the manual scheduling of all the checksum pieces. So they have the same fine control, but with a small fraction of the tuning time required. In the following demonstration, I'll run a checksum in debug mode 3 times. The first time I'll run the equivalent of the legacy or classical or older checksum and record the time it takes to run. The second time I'll run a slice of the checksum using the incremental checksum guard. I'll then compare the time it takes to run both. And then the third time I'll demonstrate that even with the finely tuned protection in place, the checksum still successfully detects a change in the code. Okay, so we've got a sample app, and you can see the sample C code and the sample guard spec. So now let's protect the app and run it. And you'll see, and we're running in debug mode so that you can see the output as opposed to taking a tamper action. And we've set the checksum to 1, which is the same as 100%, meaning that the legacy checksum is running. And also, we are calling a function repeatedly, and we're checking the entire binary. So this is for illustrative purposes only. It wouldn't normally take anywhere near as long. So we can see here at the bottom how many CPU clock cycles it takes, and in this case, we're talking 18 million, roughly. Okay, so let's use our incremental checksum to change to 1% or 100 slices. And we're going to build and run. And then we're going to see that we're roughly 14x faster. So building, running, and here we can see 1.3 million. Okay, and as we stated at the beginning, we want to actually open this up and change the file. So I've got it in VI Editor. And I'm going to change the lowercase to an uppercase because we want to ensure that the incremental checksum, even when it's split into 100 different slices, can still detect this change. So again, protecting and running. And if we scroll up, you can see that one of those slices successfully detected the hack. So we've had success. Okay, that wraps up this quick demo. To arrange a demo of this or any other security feature, please visit us at digital.ai/demo. And I thank you for listening and look forward to hearing from you.